video on Stokes theorem. I think it's Stokes or Stokes theorem. I'll just call it Stokes. So anyways, as I was saying in the video on Green's theorem, remember how Green's theorem dealt with, Green's theorem dealt with vector fields, non-conservative vector fields, so non-conservative vector fields in the plane. So this is two-dimensional, right? So this is 2D version. And Stokes' theorem, or Stokes theorem is, it also has to do with non-conservative vector fields, or just vector fields in general, I think. But this is a more generalized version of Green's theorem in that it deals with 3D. So in space, so this is 3D space. Okay, so this is a generalization of Green's theorem. As you'll see, in Green's theorem, we're dealing with the vector field being F1 and F2, right? And in Stokes' theorem, we're going to be dealing with a a vector field with 3 components, so an F1, an F2, and F3. Okay, so Green's theorem is basically Stokes' theorem, but with a special vector field that has only F1, F2, and 0 as its last component. So this is what leads you to Green's theorem, this specific case here. Okay, but Stokes' theorem, as I said, it's a more general form. So your F sub 3 is something other than 0. It can be something other than 0. Okay, so first of all, I'm going to start by showing you that, let's say, so Stokes' theorem, as I said, it exists in space, in 3-dimensional. So what we're going to be dealing with is more like surfaces and things. So an example of a surface, so like let's say here's a surface and it's bound by this curve at the bottom. Okay, so it's like a bubble growing out of this circle. Okay, so down here, let's say it's going like that. This is called C1, the little circle down here. And the whole surface itself, so this is just like a surface of some sort. The surface is called S. Okay, so in this case, the boundary of S is equal to C1. Right? So now I'll show you more examples. So let's say we have something that looks like that. That was a really ugly circle. Okay, hold on. So something like that. And it goes down and looks kind of like a tree, sort of, or like a branch. Okay, so something like that. Okay, and I'll label these. This will go this way. So C1. And then we have, see your normal going out. So go this way. Okay, and this way. So C2, C3. Don't worry about which way the arrows are pointing right now. I'll explain how you determine which way they should go. Okay, so let's say you have something like this, and the surface is everything on the surface. So something like that. These are kind of like I said, it's like a branch, or to me this looks like an artery or like blood vessels or something. Anyways, so the boundary of S in this case is not composed of one curve, but now of 3 curves. So C1 plus C2 plus C3. Okay? And like I said, I'll go over how to determine whether or not they merit negative signs in front and whether you have to reverse their orientation or not. I'll go over that later in the video. Okay? And the last example that I want to show is something like this. Okay? And you have something, it's round, okay? So kind of like a potato looking thing, like that, where you don't really have any openings, I guess you could consider it. This is kind of like a potato, I guess. So in this case, our surface is the whole entire thing going around, and in this case, it's called that the boundary of S is empty. Because it's not, it doesn't end at a certain curve like a circle here, like and go to the outside, to the air or anything. Here there's no way out, basically. So the boundary is empty, okay? So boundary orientation. So I guess later is right now when I was talking about whether you need a negative sign or not here. Well, I'll draw something on the next slide. Okay. So now we'll go over boundary orientation. Boundary orientation. Okay, so let's say again, I'll draw something like this. Okay, something like that, something like that. There's not supposed to be an opening there. Okay. All right, almost done. Okay, something like this, and this time I'll orient it this way. Okay, so this is C1, and then we have something like that, C2, and I'll go the other way on this one, so C3. Alright, and this is our S, this whole thing, and what you have to do is there's two steps. So first of all, you have to decide whether you're using the inward pointing normal, inward, or outward pointing normal vector. I'll just put it like this, normal vector, okay? So what that means is that if you're on the surface, are you pointing out like this to the outer space, or inward, in toward like the inside of the, I guess I'll call them blood vessels, so, or toward the inside of the blood vessel. So this will be given to you in the problem. So this is given in problem. So you don't have to worry about that. You just have to take that into consideration when you're determining the orientation and the curve's directions and things. So that's the first part. You just have to keep that in mind. And number two is then once you decide this, once you determine whether it's inward pointing or outward pointing, you have to make sure the surface S is on your left or right, and it's going to be left. Okay, just like Green's theorem. Remember how the when you're walking along the curve in the direction of the arrow, then the then the domain must stay on your left. Okay, so again, on your left has to be on your left. This and that. Just keep I guess you could think of it this way. In order to be right, something has to be on your left, okay? But anyways, so make sure the surface is on your left. So this is what that means is, let's say we pick inward, all right? Let's say example for this problem here. Let's say they give you inward pointing normal, inward pointing. Okay, so this determines number one, right? So for inward pointing, that means we're pointing in to the surface, in, like that, into the artery, okay? So if you're walking, let's say you're pointing in, like that, and you're walking along in the direction of the arrow, the surface should be on your left side, correct? So let's take, for example, let's look at C1, the first curve here. So if you're pointing in, so you're standing like this, okay? So you're walking along, and your head is pointing in, and then you're walking in the direction of the arrow, so that means this way. So in this case, the surface would be on your right side, correct? So I know it might be a little bit hard to visualize, but pretend you're this person, and you're walking that way, and where would the surface be? Well, the air is on your left. This is all air up here. So the surface would be on your right side. Okay. So in this case, C1 is, it has the wrong orientation currently. So that, therefore, you need it to be a negative. So to reverse the orientation. So our boundary of S is equal to, we just said a negative C1. We have to turn it around, right? So if you think about it the other way, let's say you're this person still, and now you're going to walk this way. So we're reversing the orientation. So that means you're walking this way around. And when you're walking sideways like that, the surface is going to be on your left side. Okay. Now let's look at C2. We have to determine that one. So again, I'll put this little person down here. So he's pointing in. Okay, he's happy, I think. Maybe confused as to why he can defy gravity, but you know. So he's pointing in, and he's walking in the direction of the arrow. Okay. And he looks up and he sees the surface. And he looks down and he sees air. So that means that on his left side, as he's walking, the surface is there. So that's good. We do not need to reverse the orientation of C2, so it stays positive. And lastly, let's do C3 here. So we're going to draw a little person. Okay, and this time he's walking this way. All right? So if you're walking this way, on his right would be the surface, and on his left would be space or air or whatever. So in this case, we also have to reverse the orientation of that C3. Okay? And also something to keep in mind, just a side note, once we did this, because we determined this, because we were given inward pointing normal, right? But if we were to do, again, this is just a side note, if we were to be given outward pointing normal, outward pointing, then all of the signs on these would just switch. So then we would get our boundary of S is positive C1 minus C2 and plus C3. Okay? So the signs change when you change inward to outward or outward to inward. Okay? So now let's go over a new topic. So there's something called the curl of a vector field, Okay, so let's say we're given the vector field, f arrow, of f sub 1, f sub 2, and f sub 3. So here we have a three-dimensional one, right? And so the curl of f is technically what's called this is the gradient operator. That's called. You don't need to know the terms, I don't believe. But it's an upside down triangle and crossed with, so this signifies the cross product, f itself. Okay, so this translates to, and also, just as a side note, again, you don't really need to remember this, but the gradient operator itself, it is a vector, kind of, sort of. I'm not really sure, but it's the partial with respect to x, partial with respect to y, and partial with respect to z. Okay, and f, of course, is this thing. Okay, so when you cross those, what you do is you set it up in the ijk format. So I, j, and k here. So we set up, sorry, not the f stuff. You set up the components of the gradient operator first in a row. So partial with respect to x, partial with respect to y, and partial with respect to z. And then the bottom row is just our f stuff, so f sub 1, f sub 2, and f sub 3. And the lines here just mean take the determinant. Okay, so in order to take the determinant, we just write our I. And we've done this by computing the normal vector, right? By crossing the two tangent vectors at any given point. So anyway, so we have I hat here, so then we're going to cross this product and then subtract that. So we have partial of f sub 3 with respect to y minus partial of f sub 2 with respect to z. And then we have this minus sign times j hat. And then here we'll have the opposite ones multiplied. So partial of f sub 3 with respect to x minus the other product obtained by taking the partial of f sub 1 with respect to z. And our final one is going to be plus a k hat. And we have these ones left. So these ones here make partial of f sub 2 with respect to x. And the last one here is just going to be partial of f sub 1 with respect to y. Okay? And if you noticed anything familiar, it would probably be this last term here. And this is this appears in Green's theorem. Remember? So in this case, I'll just elaborate a little bit. So remember how I was saying that Green's theorem, well, Stokes' theorem is a generalization of Green's theorem. So in the case that f sub 3 is equal to 0, if f sub 3 equals 0, then if you think about it, then these here, well, all of this is going, basically these terms would go to 0, okay? And you would just be left with this here. All right, so that's just, again, a side note. But anyways, a different way to write all of this like I hat, j hat, k hat stuff, is the following way. So then you would just write partial of f sub 3 with respect to y minus partial f sub 2 with respect to z. And then here the minus signs flip, right? So we could get partial of f sub 1 with respect to z minus partial f sub 3 with respect to x. And our last component stays the same. So then partial f sub 2 with respect to x minus partial f sub 1 with respect to y. So this is quite a handful, and it might be a little bit hard to memorize, but I've found a useful pattern, I guess you could say, and you'll probably see it as well. Just when I would write these, I would think 3, 2, 1, and then another 3, 2, 1, and that corresponds to the subscript on the F components, right? So 3, 2, 1, 3, 2, 1 there, and then on the bottom, I just wrote y, z, z, x, x, y. Just remember that pattern, and you'll be pretty much set to set up the curl. Okay? And then you have to, of course, you have to remember the minus signs go in between, and it's basically an alternating of minus sign, comma, minus sign, comma, minus sign. Okay? So anyways, that's how you set up the curl. So let's do an example. So we're going to calculate the curl of the following vector field. F arrow equals x times y, comma, e to the x, comma, y plus z. Alright, so let's set up the curl. So we have curl of f equals, so this is also f sub 1, f sub 2, and f sub 3. Alright, so this is going to equal the following. We're going to have our 3, 2, 1, so 3, and I'll just write them in a little bit abbreviated format. So F3, and then an F2, and then we need an F1, and then we need another 3, another 2, another 1. Okay, so that's the first thing I would do. And then you add in the letters, the variables that you're differentiating with respect to for each one. So for this one, we're going to say it starts with a y, right? A single y. And then it goes to z, and then another z, and then it goes to x, and finishes up with a y. Alright, so now we're almost done. Now we just need to alternate signs. So this is a minus sign first, and then a comma, a minus sign, comma, and a minus sign. Okay, and then you have your formula for the curl. Okay, so now all we need to do is actually compute the curl. But half the battle is actually remembering how to do it, so, or the formula itself. So that was good. And then now we're just going to take, what this signifies is the partial of f sub 3, so y plus z, with respect to y. So something like that, right? So we're going to have that for the first one, and then minus partial with respect to z of f sub 2, which is e to the x. And then we have the partial with respect to z, but this time of f sub 1, which is x times y. Alright? And then minus partial with respect to x of f sub 3, y plus z. And continuing, we had partial of x. Well, it looks like a 2. Okay, with respect, partial of x, partial with respect to x of f sub 2, which is e to the x. And finally, we have the partial with respect to y of f sub 1. So that's x times y. Alright, so now we just compute the partial derivatives. So we get, for the first one, that's 1, and then minus 0, right? Because there's no z's in here. And then the next one, we get a 0, and then minus another 0, because there's no x's in this one here. And for here, we have just simply e to the x, and then minus an x. Okay? So the last, our final answer is going to be 1, comma, 0, comma, e to the x minus an x. Alright? So that is the curl for this vector field. Alright, great. So now we'll move on to something a little different. Well, not really that different. It's related. So I'm just going to say, if we do have a conservative vector field that means that f is equal to the gradient of v, where v is our potential function. Remember, potential function. This is our scalar potential function. Okay, so what happens in this case is that the curl of f, oh, hold on, I've got an L here, curl of f is equal to the curl, I can't type, I'm not even typing, okay, curl of the gradient of v, which is equal to the 0 vector. Because, and the reasoning behind this is because the cross partials that make up the components, of the curl of f, are equal to 0. Okay, so basically what this is saying is that when we have something like the conservative vector field, so this is when you have a conservative, I'll draw it down here. So when you have conservative vector field, when f is conservative, that means that the cross partials condition is also satisfied, right? Remember that? So cross partials have to be satisfied, that condition, are equal. So with them being equal, when you subtract them with the curl, so when curl of f equals the following, so the formula says that we take the partial of f sub 3 with respect to y first, and then minus partial of f2 with respect to z, and then the next one is, I'll just set these up, so z again minus f3 and an x, and then f2 and an x minus f1 and a y. Okay, so when we have cross partials being equal, that means that whatever this is equal to this. So that means you get 0 or something minus something. I'll just call it a or whatever. So a minus a equals 0, and then this will be something, and that'll be something, and those will be equal. So that means that this is 0, and also this equals this, which is like a c minus a c, and that's 0 as well. So we would just get that the curl is the 0 vector. So 0, 0, 0. All right?